In this video, I want to show us how to solve some tricky integrals using u-substitution. So remember the idea of u-substitution. Whenever you have the antiderivative, you're trying to find the indefinite integral of the antiderivative of f of g of x, well, I'm also going to need a g prime of x, so the derivative of the inside. What I do is, in order to help me think about this, to organize it in my mind, I set the inside function g of x to u, and then the derivative of u becomes the derivative of g of x times dx. This is my du. So du dx is g prime of x, so du is just g prime of x dx. Which then tells me that this is just the function little f of u times du, which then has as its antiderivative, the indefinite integral, big F of u plus a constant. And then I end by changing it from the language of u back to the language of x and say, so that's just big F of g of x plus a constant. Those are the steps of u-substitution. And let's see this in practice with two tricky integrals, two integrals that probably be pretty difficult to solve without u-substitution. For the first one, consider the indefinite integral of x, I don't know, let's make it x cubed times the square root of, I don't know, x squared plus 1. That looks good to me. Let's try to find this guy. Okay, I just made this up. It looks somewhat similar to maybe problems we looked at in the previous videos, but a little bit different. So this I think would be pretty hard to do. It'd be hard to jump from the first step all the way to the last step. U-substitution really comes in as our friend here. So what are we going to make equal to u? Well, the trick is, can you find an inside function, the function inside of another function? And in this case, the inside function jumps out at us. It's just the x squared plus 1, because it's inside of the square root. So what is your du? Well, your du dx, the derivative of u with respect to x, would be the derivative of this guy. It's 2x. You think du dx is this, and then you move the dx over. So you get du is 2x dx. And then you look up here and it's like, do I have a 2x dx? I don't quite have a 2x dx. I have an x cubed dx. And if I wanted to, I could break off one of these x's to give me, break off from the x cubed one of the x's. So I have x squared left behind. And I pull over one of the x's over here, so I have an x dx. So here I have an x dx piece, which is pretty close to 2x dx. I just don't want that 2 there. So I'm going to move the 2 to the other side to get 1/2 du is x dx. So now you can start doing some u-substituting. And you're like, okay, so my square root of x squared plus 1 is going to become just the square root of u. And the x dx, that's going to become just a 1/2 du. So I'm going to put the 1/2 out front. But wait a second. What happens to my x squared? I don't know what x squared is equal to. So like, what should x squared be? And this is where we have to be clever. We're going to come back here. We're going to say, well, if u is x squared plus 1, that means x squared is u minus 1. Right? I just move the 1 to the other side. So I'm going to replace that x squared with a u minus 1. Now maybe it's not obvious that this is simpler than it was before, but notice what we can do now. If you think about u, the square root of u, as being the same thing as u to the 1/2 power, then when you distribute, this is just u to the 1 times u to the 1/2. That's u to the 3/2 to the 1.5 minus u to the 1/2. And this is now something that we can find the antiderivative of. I don't know how to find the antiderivative of this, but this is something I find the antiderivative of, because I can just use my power rule. The antiderivative of u to the 3/2 is I increase the power by 1. I'm going antiderivative, so it's going up by 1 to 5/2. And I put the reciprocal out front, so 2/5, minus increase 1/2 to 3/2, put the reciprocal out front to 2/3, plus c. There you go. We've solved it. Well, we solved it in the language of u's. They asked us the question with x's. the answer is in u. It's probably polite for us to answer in the same language they asked the question. So we're going to translate this from the language of u's back to the language of x's. So wherever I see a u, I'm going to replace it with x squared plus 1. And also along the way, I'll distribute this 1/2. So 1/2 times 2/5 is just 1/5. Those 2's cancel. So it's 1/5 of u, x squared plus 1 to the 5/2, minus 1/2 times 2/3 is 1/3 of x squared plus 1. I'm changing my u back to x squared plus 1 to the 3/2 plus c. So there you go. Here's the antiderivative. And I don't know, maybe if you're clever, you could have gone directly from here to here, but it sure seems like introducing this u-substitution really helped us with this. Let's look at one more problem where we can use u-substitution. And so the problem is going to be, I want to find the indefinite integral. I want to find the antiderivative of 1 over 3 to the x plus 3 to the negative x dx. How can we do this? And this is a pretty wild function. I don't think there's any way you could just guess the derivative of what equals this. It'd be pretty impressive if you could just guess it. So we really need to do u-substitution. And the trick is for u-substitution is you always want to be trying to think of like, what is the function inside the other function that you can make your u, and then you hope that you can find the derivative of u kind of hanging out somewhere else. So you can simplify this to just the antiderivative of just some little f of u, something much easier to solve. And here, it's maybe not at all obvious what the u should be. You know, like, I don't know, you might try and make the whole bottom u, so it's just 1 over u. But you won't have the bottom, the derivative of the bottom isn't laying anywhere, so that probably isn't going to work, right? It's not obvious what the u should be. You might try a couple things and you know, fail a couple times before you get lucky. But I'm going to suggest that we try to make u just this piece right here, this 3 to the x piece. Now, at first, it's going to look like this is just a mess, because what is your du? Well, my du, or more in particular, if I want to find du dx, remember, we'll remove the dx over the end, but to find du dx, I'm going to find the derivative of this with respect to x. And you have to think back now, the derivative of e to the x would be e to the x. The derivative of 3 to the x is 3 to the x with an extra little constant out front, with an ln of 3 out front. So it's an ln of 3 times 3 to the x. So what is du? Well, du is just move that dx to the other side. Du is just ln of 3 times 3x dx. And like nowhere do I have a 3 to the x dx, or ln of 3 to the x dx. I mean, ln of 3 is just a constant. That's just a number. It's, you know, a little bit bigger than 1. And so you could move that to the other side if you wanted to. You can make it 1 over ln of 3. Du is 3 to the x dx. But I don't have a 3 to the x on top. You know, I don't have a 3 to the x on top to have 3 to the x dx. So this might seem like we're at a dead end. I could change this guy here into a u, but I don't have a 3 to the x up top. But we're not at a dead end, because there's a trick that we can do. And the trick is, we're going to multiply the top of this function by 3x, by 3 to the x, by 3 to the x. Because I want to have a 3 to the x dx. But you know I can't just multiply the top of a fraction by 3x, that's changing the problem. In order to avoid changing the problem, I also need to multiply the bottom of this by 3 to the x. Let's see what we have now. The problem now becomes, find the indefinite integral, the antiderivative, of 3 to the x over, what happens when I times this by 3 to the x? Well, 3 to the x times 3 to the x is 3 to the x squared, plus, what's 3 to the minus x times 3 to the x? Well, when you multiply, you add the exponent, so negative x plus x is 0, so it's 3 to the 0, that's 1. Ah, here we go. This now becomes the antiderivative, or the indefinite integral, of 3 to the x over 3 to the x squared plus 1 dx. It still looks pretty messy, but now we're actually in a pretty good place. Because this 3 to the x dx on top, this 3 to the x dx on top, you can think it can be replaced by a 1 over ln of 3 du. So I'm going to replace those two with a 1 over ln of 3. That's just a constant, so I'm going to pull it out. and a du. I'll just call it 1 on top now. 1 times du. So 1 over ln of 3 times 1. I have a 1 there. You have a 1 times du. And what do I have on bottom? On bottom, I have 3 to the x, which is just u. So on bottom, I have u squared plus 1. Okay, forget about the constant term for now. You'll come back in a second. But let's just focus on what we're trying to find the antiderivative of. What is the antiderivative of 1 over u squared plus 1? Or said another way, the derivative of what is 1 over u squared plus 1? So you have to think back now, but this is actually it's a derivative of a special function. This is just the derivative of tangent inverse. Tangent inverse or arctangent of u. The derivative of arctangent of x is 1 over x squared plus 1. The derivative of arctangent of u is 1 over u squared plus 1. So this antiderivative is just tangent inverse or arctangent of u, the inverse function that corresponds to tangent. And then I have this constant up front, 1 over ln of 3. And of course, plus c at the end. So there you have it. Although we're not done yet, since we're asked the question with x's, we end by putting the answer back into the language of x's. It's 1 over ln of 3 times arctangent, tan inverse, of u is 3 to the x. 3 to the x plus c. And you can check, find the derivative of this, do out the chain rule, and sure enough, you just go through this backwards and get to the original problem. And so there's probably no way you would have been able to guess this by looking at the original problem. But by going through this u-substitution process, we're able to solve it. We're able to find the antiderivative.